I'm guessing most of you, if not all of you, use Unity, right? Yeah. So every time the level is built, the game engine will just kind of go through. It'll go, okay, which way will I go? I'll go this way. I'll pick a random room. Go this way. Pick another random room. And we just kind of control how big the room is, or how big the level is, and how many branches off the main path it will take. And then within the each room, there's a bunch of spawners, and that can, that randomly picks what it's going to spawn as well, with kind of weighted. There's more chance of a monster spawning, say, a chest or something like that. So basically, you run around and you shoot your head to attack things. And let's see if I can get so the main kind of mechanic is you can kind of swap your head out, and when you get a different head, it'll do weird things. Are you looking at the pro features, are you?
Forcing to change perspective?
That's me controlling that, yeah. So we kind of had it built before where all the rooms were they didn't have high walls like that. So, we did have the switch around, but we were kind of toying with the idea of maybe not being able to do that. But it kind of didn't work out, so we're back to switching the camera around.
Here we go.
Cool. Might have to restart it.
Everybody
Working okay?
Yeah, it's working okay. I think it was just whatever the
Turn the light off. I won't bother taking the video on because it's actually too dark.
Okay.
It's playing really well on that laptop, actually, isn't it?
Yeah, Robbie changed a lot of the way the core of the game works, and it's running way smoother than it used to. Okay, so I finally got a different head. So this one's like really hard to control. You just have to kind of swing it around like that. But it's way more powerful if you do connect with it.
And what questions have you guys got for Ralph? About making games in Unity or whatever.
It's like C# or C++?
C#, yeah.
So what's your proposed release date?
We're hoping to go on to early access in the next 2 or 3 months. So we're pre-approved on Steam as it stands. So we could release it tomorrow, but we want to kind of get it to a better place.
Is it kind of ready to release, do you think?
Not yet.
It's not far off it though, maybe.
Not too far off it. No.
Cool. That's awesome.
Yeah.
So I suppose the other question that everyone's probably asking themselves is where can they buy it now?
You can buy it on our website.
Take this down, everybody.
BitSmithGames.com.
And you can pre-order it.
BitSmithGames.com. Yeah, pre-orders are up now. So yeah, we're hoping in the next couple of months we'll be out in early access.
Great.
Is it coming to any other platforms, or is it just Steam?
Sorry?
Is it coming to any other platforms, or like indie stores on?
We're gonna put it out as many places as we can. Yeah. We're gonna leave with Steam just because it's kind of the biggest, plus it has that kind of the early access thing, so we can get it out there a bit earlier.
How do you store your scene? How do you store all those positions of all those things?
Okay, so if you're looking at the scene before you play it in Unity, it's literally just one game object with a game manager on. And when it runs, that game manager just spawns in everything else on the fly.
Cool. It spawns it though. How does it know where to spawn it? Is it in a file or something?
Well, I think as far as I know, Robbie would be better equipped to answer this, but as far as I know, it'll spawn the first room at 0, 0, 0, and then
Okay, and then it proceeds
from
to
there
generate
it'll go on.
positions. I
Yeah,
see.
yeah.
So does it hold them all in a giant array? You just plug them into each other?
We just have a bunch of folders in the resources folder of Unity, which it means you can just pull it in directly from there. So
They're just going to be pulling prefabs.
yeah, exactly. Yeah, yeah.
That's awesome. So the other question I'm sure is on everybody's mind is does it work with the Oculus Rift?
It does actually. It's really easy to do it in Unity with Oculus. Like they have a little library you just drop in and throw in a camera and it works. So we tried it once. We haven't really kind of developed it to.
It's not a mode really for the game, I suppose.
Yeah, I mean, yeah. No, I think we should put it in though, personally.
Yeah.
Why not? Like,
You can use it as an extra feature.
yeah.
Swing your head around to control it, is it?
Yes.
Wood head trap.
Yeah, that might be an idea.
Yeah, I suppose you could just have, like, I'm sure there'll be not first-person games that are Oculus.
Yeah, I saw one actually when I was over at Unite there, and people were saying great things about it.
Yeah.
So I mean, yeah, a lot of people just kind of go, oh yeah, Oculus, it's got to be first person, but because I mean, obviously you'll get the 3D effect.
Yeah.
The other part of it is that like there is kind of an exploration element to this game. So if you're trying to look for the exit, you could look around.
Get rid of having to manually switch perspectives and stuff like that. You just turn your head first.
Yeah. I mean, I don't know if you could maybe go the whole way around, but it's definitely worth
You'd
it.
have to do both. You'd have to allow them to rotate their head.
Yeah, I
Just
think
use
so,
the
yeah.
rotor as well.
Is there no gesture, like head gesture type thing built into the Oculus?
It's really
I'd say
disorientating if you
us,
use it.
yeah, every time you're looking at the ground. Yeah, I'd say that would be a tough one. So I just got another skull cap. This one has a special ability, so when I press Y.
Tell us about the audio.
So I did mostly audio, the sound effects and that, and I'm using an external program called Wise, which will just you can kind of build it without testing it all the time in the engine, and then you can you just plug it in and you call an event, and it makes things a lot easier. Unity's audio is a bit limited, really.
Who's doing your soundtrack?
The soundtrack is by Ben Prunty, who did FTL.
You play FTL?
Yeah.
Yeah, so I don't know if you can hear it. We've got 2 tracks up from so far, they're both awesome. This is another kind of weird one. So this just kind of turns everything into isometric view. So not all of them are going to be beneficial. Some of them have a kind of...
We better do some C++, huh?
Yeah. Leave that there anyway. Maybe
Yeah, thanks, Ralph.
You want to
I
play it
think I
later?
pre-ordered. Or back to a Kickstarter or something. Back to a Kickstarter isn't Kickstarter.
Yeah.
Yeah, I know I pre-ordered this week.
Cool.
Cool. Thanks, Ralph. Thanks,
All right.
everybody. Give
No
me a
worries.
big deal. So there's a little tank going around the outside. All right. Let's think about a little bit of math that is required to get that tank to move in the direction in which it's rotated to. So, what are we storing about the tank? What state has the tank got? Position. Yeah, so it has a number of things. It has a position. What else state has the tank got? It's got its look vector. And what other state has it got? Speed. It has speed. And what's the other one it has? It has a value called rotation. And what type is rotation? It's in radians, so it's what? It's a float, isn't it? And the rest of these things, the look and the position, what are they? Yeah, these are 2D vectors. And what about the speed? Yeah, it's a float as well, okay? And what are we doing each time around in the update loop for each one of those guys? So what are we saying? Pause plus equals to get it to move in the direction in which it's looking.
Speed times look times
Yeah.
time delta.
It's going to be the speed. Where's the yeah. It's going to be the speed multiplied by the look vector multiplied by time delta, and what else? Oh, why the rotation? Actually, that's all we need to do. So you see, it's very important that this is the state we're keeping track of, and this is how we what's called integrate the states. So this is what we need in our update method. Sorry, it's position plus equals to the speed multiplied by the look multiplied by the time delta. So even though we're controlling it with look, even though we're controlling it with this rotation variable, we're using this look vector essentially to calculate the new position each time step. Everybody kind of following this okay? So then the challenge is, right, getting the tank to move around in those 4 directions. The challenge is going to be setting this rotation variable here. And from this rotation variable, we then go and calculate the look vector. And that's how we get it to move in the direction in which it's looking. Does everybody follow that? So then the little bit of maths we need to work out is basically how to calculate this from this. By the way, everyone's really quiet. If this is stuff you already know, just say so and I'll move on to the next thing. Or if you want me to go through it. Yeah, okay, cool. But just give me some feedback and let me know, okay? Just say, yeah, I'm not understanding that, or I am understanding that, or whatever, okay? Or ask me some questions. So that's the challenge. Okay, so the challenge is really easily addressed if we understand a little bit about what's called the unit circle. It's really simple. So essentially, this is a 2D thing, and in this 2D thing, I've got the x-axis and the y-axis like that. And I have my tank somewhere in the scene like this. The sprite we know from this example, the sprite is given to us pointing straight upwards like this. So in other words, if I apply no rotation to this tank, it's going to point straight upwards. Does that make sense? Okay. The challenge is then calculating in which direction we want to move the tank if I apply a rotation to it. So let's say I apply a 90-degree rotation to that tank. What direction is it going to move in? What's that? If I apply a 90-degree rotation to the tank, what direction will it move in? It will move in this direction here, right? So if I was to think about that in terms of a vector, what would I add to the tank's x and y to get it to move in that direction? What would I add to the x? You're going to add 1 to the x, right? And what would you add to the y? You would add 0 to the y. Okay, if I did a 180-degree rotation, what way would that vector look?
Straight down.
It would look straight down, so I would be adding 1 to the x and 1 to the y.
1 to the y, nothing to the x.
I would be adding 0 to the x and 1 to the y. And what would I be adding if I was moving 270 degrees off in that direction? I'd be looking at -1 and 0. And then, of course, no rotation means my look vector should be what?
0, 0.
Should be 0 and -1. 0 and -1 because the y direction in this example is straight up, yeah. So that means I'm going to subtract something from the y and I'm going to do nothing to the x. Does everybody see that? Everybody understand that? So now we're looking at the relationship between the angle, which is 90 degrees or 180 degrees or 270 degrees, and the direction in which I'm going to, or this variable here that I'm going to use basically to integrate the position each time. So we can draw up a little arrow like that, and you can basically draw a circle around it like this, okay? And then that's called a unit circle. It's called a unit circle because the distance, the radius of this circle is going to be what? It's going to be 1. So the distance from there to there is 1. That's what we call it a unit circle. And then what we do is we draw in the angle that I want to rotate by. So let's say I want to rotate by theta radians like that. Another thing we have to decide is, do our rotations go clockwise or counterclockwise? They go clockwise in this example, but they don't always go clockwise, right? So we have to know, we have to decide which way. And it depends, you know, in OpenGL they go counterclockwise. But in these examples they're going to go clockwise. So, rotating by that, huh?
Is there any particular reason why OpenGL goes counterclockwise, or just anything?
I think no, I don't think there's a particularly good reason. It's something to do with the fact that the Z goes away from the screen instead of towards the screen or something like that. I don't know. It's just you have to keep it in mind when you're doing certain calculations, right? Anyway, so that's the angle I'm rotating by. So the challenge is then figuring out what's the x and y that I need to add, you know, in this here. And you can calculate it as being the x and y, the point on that circle. Can anyone tell me why it's not 0 and why it's not 1 and minus 1? If I wanted to go 45 degrees, why is the look vector not 1 and minus 1?
Because it goes less than the unit circle.
Yeah, because 1 and minus 1 is what? It's actually not on the unit circle, it's a value up here. So when I do this little calculation, that means if I go in this direction here, I'm going to be moving faster than if I went straight up in the cardinal directions. So we can solve this using a little bit of trigonometry. Looking at this thing here, I can see that there's an angle, and that's the opposite side of a triangle, if I wanted to think of it like that. And the opposite side of that triangle, in fact, is the x value that I'm looking for. And then this side here is actually the y value that I'm looking for. Did everybody follow that? You can see that, that's the right angle triangle, that's the way it looks. So, by our kind of rules of trigonometry, this here is going to be what? That's going to be 1. So the radius of this, because it's a unit circle, is going to be 1. So looking at this example, if I was to try and calculate this look vector, I could say that the sine of the angle that I'm rotating by is going to be equals to the x value over the radius. And in this case, the radius is 1, so it's just equals to the x value. So, you remember all this from second year? Yeah. So then the other thing then, looking at that, is the cosine, which is the adjacent of theta, is going to be equals to the y value. But we know in this example here that our x is positive, but the y is negative. So if I wanted to move up in this direction here and rotate by this amount, I would have to be subtracting from the y. So that's the little bit of maths. That's called the look vector, and that's called the unit circle. And that's how you calculate the unit circle from the angle of rotation. And it changes depending on which way the sprite points if you apply no rotation. And it changes also based on whether your rotations are clockwise or counterclockwise. Is that okay with everybody? So now we can code that up. When we look at it, let's see, that's exactly what I'm doing. The x equals to that, and the y equals to that. Do you want to do a small trigonometry problem just to make sure everybody knows? Do you want to do one? Or is this okay? Can we move on? What's that? Cool, let's move on. Alright. Is it because your brains are not ready for it, or because you just know it? Too early. Okay, getting mixed signals here, right? Yeah, so that's it. And then the last little bit then we need to worry about is like what causes the... So I can basically take this rotation and I can apply it into this and calculate that. So then, what do I have to do? What's going to control whether I change the rotation amount? What's going to change? What?
Your position.
Your position, and specifically what am I going to do? I'm going to write an if statement. And I say if a position goes too far, I'm going to add 90 degrees to the rotation, and the thing will just work. So let's take a quick look. So here's the AI tank. I have a little draw method here. And yeah, so there we go. My position, this is hard coded, you know, but it's just the way it works. So first of all, I'm checking to see if I go too far to the left. If I go too far to the left, that makes me, that's because my sprite is, what would my sprite have to be? What's the dimensions of my sprite? Looking at the code above. Try again. Try again, I think it's not 20. Oh, no, you're right, it is 20 by 20. No, hang on, is it? You would have to decide, is the position the top left, or is it the center of the sprite?
Yeah, 40 by 40.
I think it's probably more likely to be 40 by 40, because I'm pretty sure the x and y coordinate is the center of the sprite when I do the rotation. So that's it. Okay, so then, if I go too far to the left, I set the x equals to 20, set the rotation to be equals to 0. So what does that mean? If I go too far this way, set my rotation to be 0 radians, so I'm going to go straight up. If my y is less than 20, then that means I'm at the top of the screen, and I want to go which direction?
That's your right.
Oh, okay, so that's pi radians. So, hang on, half pi, yeah. So straight up, half pi, pi. And so on for the other things. And they're just hard-coded numbers.
What did you do with that one instead of just using the radians function?
What radians function? Oh, the radians functions in GLM.
90.
And because they're just constants, that's just a different way of getting those pi constants. Of course, you can do GLM colon radians and pass it the degrees value if you prefer. But I think that's just the same. Okay with everybody? Alrighty, so that's our first bit of maths. Is everybody excited? You can now solve problems. And you definitely know all this, and we don't need to do a problem. You can just do it. Everyone? If I was to give you two positions of objects in the scene, and I told you how much rotation it would take to rotate one to point at another, you'd be able to solve that, wouldn't you? Cool. Great. Moving on. Okay.
But the
Awesome.
exposition, why,
Ah.
when the tank is going to the left, why do you put the exposition if x is less than 20? If you had it at 0, the tank would still stay on the screen, because the sprite is generated from the top left.
No, but I think the sprite is actually generated from the center. I think that x and y is the center of the sprite.
I think it is top left though, because when you were playing it, it was further
Yeah.
away from the left edge than the right edge.
Okay, let's try it. Oh, what the hell does that one even mean? Anyway, we'll just run it and see. Let's make sure we know. Maybe you're right. But I don't think so. I think it is the center of the sprite. But I am open to correction on that one, yeah? You could be right. You could be right. Shall we move on? Regardless? Everyone happy? Cool. Yeah, so sometimes we might use trigonometry to solve problems in games, to get things to point at other things, but I take your word for it that you know that. Grab a page. This isn't your Okay, all this is about algorithms in C++, right? So here's the first thing. So we're already a little bit into the world of the vector. We've used a vector already, and we can say that now that there's this thing in C++ or in maths called a vector. And what are the properties of a vector? What if I was to say make a vector of that and use that first? Like, what would you use? What does it mean?
Direction and velocity, isn't it?
Mm-hmm. A vector theoretically has lots of things, but like, what's the basically the core definition for a vector?
In maths, it's 2 digits, but in physics, it's force with direction.
Sure thing. Yeah, in fact, the mathematical definition is the right one. The physical one is just what we're using that thing for. So yeah, okay, so in maths it's 2 digits. In actual fact, a vector is just a list of numbers. And in C++, C++ has 2 different types of vectors. It has vectors which are numbers like x, y, and z and stuff. So when I do GLM, for example, colon, vec2, I bet you can guess straight away what the fields in that class are going to be. If I was going to go, hey, what's it going to have? It will have an x and y coordinates, right? So that's a.x and a.y. And there are 2 properties of that vector. So now, vectors are a list of numbers. Is there a limit to the number of numbers you can put in a vector? Not really, not mathematically. They can be as long or as short as whatever you want, right? So it's just a list of numbers. The type of vector, yeah, that we use for maths are typically these type of vectors. But C++ also has something like this, std colon vector. And what do you think this type of vector is then? It's also a list of numbers, but it is more like a what? It's an array. So this is a vector as an array of numbers, okay? And in fact, it's an array of whatever, because you can store numbers or you can store whatever in conservative units, right? So the properties that vectors have, like we've said already, vectors got an x and y. What kind of other properties does a vector have?
Speed and direction.
Yeah, essentially it's just an x and y, but you could basically say, yeah, speed and direction. Direction is what, an angle?
Yeah.
Okay, it could be speed and direction. But just in terms of a vector, what do you think you can do with it? Vector's got those 2 parameters. The fact that it has an x and y means we can do what with it? Yeah, we can add vectors together, okay? So here's the first thing you can do with a vector. You can take 2 vectors and add them together. What happens when you add 2 vectors together? You get a vector back. Very important to know what type of vector. How does the operation actually work? If I was to go GLM colon vector 2, A and B, and I go C equals A plus B, what will it do?
Add the x's and add the y's.
Got it. It just adds the x's together and adds the y's together. In order for this operation to be valid, what do we have to say about the 2 vectors? They have to have the same? Yeah, what's that called? It's called the dimensionality of a vector. So they have to have the same dimensionality. In C++, you know, you can only add a vector 2 to another vector 2, or a vector vector 3 to another vector 3, because what would you do with the extra bit of the vector? So that's adding vectors. Subtracting vectors is pretty much the same thing. To subtract two vectors, you just subtracted the x's, subtracted y's together. Let's say if I pick two vectors and I said one of them was 10, 10, and the other one was 100 and 100, they clearly have something in common, don't they? What would they have in common? Yeah, they're both 2D vectors, both of the same dimensionality. What's that? They're both base 10. Anything else?
Same types.
They're both the same types. Yeah, what's the relationship between them?
Are the same proportions then?
They're in different proportions, aren't they? What can you say about the difference between the two vectors?
It's the same direction.
It's the same direction. What have we done to make one vector into another vector? You've multiplied a vector by a scalar. Okay, so you can multiply a vector by a scalar and it retains its direction, but it changes what about the vector? Apart from the x and y, it changes the magnitude of the vector. Alright, so these vectors, this is another operation we can do. You could do I don't know, just float f. And you can go a equals a multiplied by f, where f is a float and a is a vector, and it will take the vector, multiply the x component by the float, multiply the y component by the float, and then that's what it will do. Is that okay with everybody? So we can scale vectors, multiply them by scalar. And then you guys got into something there, you said that these vectors have different magnitudes. What does the magnitude of a vector mean, and how would you calculate such a thing? What does it mean? What's the magnitude of the first vector?
Is the magnitude difference between two things?
No.
Is it 10 and then the difference together?
Try again. How would I know the magnitude of the vector? Like, here's an interesting question for you, right? Imagine a car is traveling in, you've got some car and it's traveled maybe 5 units on the x-axis and 3 units on the y-axis. Alright, so you can see that you can describe this problem in 2D. You want to know how far has it traveled, and then that would tell you the magnitude of that vector. You see that? So how would I calculate it?
Distance from 0.
It's the distance from 0, right? So the length of this vector is going to be what? How would you calculate the distance from 0?
The distance one.
So, yeah, this is going to be the square root of
x2
x squared plus y squared. So that's how we calculate the magnitude or the length of the vector, okay? And this is another property of a vector. I'll show you how that looks like in GLM. I think it's just, it's GLM. I think it's GLM. Yeah, GLM colon length. It's not a property of it, right? And you pass in the vector A, and it's going to return you what? It will return you the scalar value, okay? So that's those things. Next thing we might want to do, there's a property of certain types of vectors. You remember we were doing the unit circle vector earlier on? We're looking at the look vector. That has a particular property. What's the property of that? The magnitude of that vector is going to be what? It's going to be 1. The distance from the center point to the outside of the vector is going to be 1. And yeah, so that's sometimes we have a vector like this, and I want to basically get it so that the length of that vector is 1, and I can make it into a unit vector. I can make it into one of those ones. So that operation is called normalizing a vector. So it's GLM colon normalize. And you pass in the vector A, and it will return you back a vector, which is the normalized version of that. What does it mean? How do we calculate it? If you had to write a normalized method or something, what would you be doing to make its length equals to 1? So say that vector there, 10, 10. What's the? Here, let me give you a different one, an easy one. Take that vector. If you normalize that, what's its value going to be? What's the x and y going to be?
0.
What would the x be?
0 plus 1.
What would the x be? Try it again. I want that vector to be in the same direction, but I want its length to be 1. So how would I do that?
0.
What would be 0? What would be 0?
10 would be 1.
10 would be 1, and the y would be
0.
Yeah, okay. So you have 1 the vector of that. And you can see that that's normalized that vector. What did I do to make it into that normal vector? What did I do to it?
Divided by
Divided by its scale.
Why did I divide by? Why did I pick 10 as the number to divide it by?
Is it scalar?
Because it is the
length.
It's the length of the vector. Okay, so you pick the length of the vector, you divide the x component by the length, the y component by the length, and that's called normalizing the vector. It's another important vector operation. So we can take the vector a, and if we have a, and we want to normalize it, what you do is you divide by the length of a, and mathematically that's how you write the symbol for the length of the vector a. So it's just a pipe down either side. But in the GLM maths library, you just go a equals GLM colon normalize. Okay, cool. So we can add vectors, we can subtract vectors, we can multiply vectors by scalars, we can normalize a vector, we can calculate the length of a vector. We can do lots of great things with vectors now. Is everybody really happy with all the cool things that we can do with vectors? Can we even solve a problem? No, that's not solve a problem yet. Let's do one more thing that we can do with vectors. And then I might blow your minds with a cool thing that we can do with vectors. You love it. You will definitely love it. It's the most coolest thing you're going to learn all the semester. And if you don't learn anything else this semester, but you learn this, you probably pass your exam. Okay? So, we can multiply vectors by other vectors. Alrighty? So if I had the vector A and I had another vector called B, I can go C equals A. In fact, you could do this mathematically, but you can't do it in code. You can multiply these two vectors together. And in fact, there's 2 ways to multiply them. The first way is called the dot product. The dot product of 2 vectors. And in order to get the dot product of 2 vectors, what you get back, first of all, is a scalar. So you get a float back. And say you want your float f. So you'll basically get f is going to be equals to a dot x multiplied by b dot x plus a dot y multiplied by b dot y. So you multiply the x's together, you multiply the y's together, and you get back. You add them both together, and you get a scalar. A rather pointless and useless piece of information, you would think. Why would you possibly want to multiply the things like that to get a scalar back? And the answer is, I'm not going to do the derivation for this because it would take too long. You can trust me, I'll put the link up to the Khan Academy video where it shows you the derivation for this. If you have 2 vectors in a 2D space like this, right? You've got one vector which is drawn like this, you've got another vector which is drawn like this, and if this is A and if this one is B, are you ready? Have your minds blown? Okay, I'll proceed regardless. Theta, which is the angle between those 2 vectors, is equal to the dot product of A and B divided by the length of A multiplied by the length of B. Sorry. Theta equals the inverse cosine of these guys. So will everybody please write this down on a page and never, ever, ever forget it. If you're going out at the weekend and you plan to meet a girl, just say this to her as you're like chatting wine, and she'll be so impressed. She'll really just, I've tried this, it works. Even try it with your mom. Phone your mom tonight. Guess what we learned in college today, Mum? We learned this really cool formula that we can use to solve all kinds of interesting problems in computer games. It's the best thing ever. Is that okay with everybody? So, if you believe me, let us try a simple example, okay? Using this formula here, here's 2 vectors. Tell me what theta is going to be. Here's 2 vectors, right? Let's say the vector is 0 and 100, and the vector 87 and 0. And work it out, put them into that formula, and tell me what angle you get between those 2 vectors. Some of you will know straight away what the angle is, but regardless, just do the little problem and tell me what you get. Pen and paper and a calculator. And if you don't know the answer, work with the person sitting beside you. Do you all know each other? Introduce yourself to the person sitting beside you there. Say hello, shake hands. Hey, how's things? Exchange gamer tags. Work it out. Somebody tell me what the angle between those 2 is. And yeah, so A dotted product with B is going to be 0 multiplied by 87 plus 100 multiplied by 0. So you basically have 0 multiplied by 0, which is going to be 0. So you have 0 on the top line there. It doesn't matter what you have on the bottom line because anything into 0 is 0. So now we have the inverse cosine of 0. And the inverse cosine of 0, if I type it into my calculator or into my computer, the inverse cosine of 0, you get 90 degrees. And you can see, obviously, this is the same as the vector 0 and 1 because it's the same as the vector 1 and 0. If you normalize them, that's what you get. So now we have a way to calculate angles between vectors. An interesting property, we've kind of discovered something cool. What happens if we have two vectors and we dot product them together and we understand that the answer is 0? What does that tell you about the two vectors?
90-degree angle between
They're perpendicular. Okay, so if A is perpendicular to B, when we do this thing, we will get an answer of, in fact, the cos of this means that this is 90 degrees. Cos of this is 0. So that's 90 degrees. Cosine of 90 degrees is 0. Here's an interesting one. Let's pick two other vectors, right? Let me pick the vector, let's pick the vector 1 and 1, and the vector 5 and 5. Get the dot product. In fact, that's not a good one. It's 5 and 10. Do those ones. Okay, so what we get here is 1 multiplied by 5, which is 5, plus 10. So you get 15 on the top line. And on the bottom, this vector is going to be the square root of 2. It's going to be the length of it, isn't it? Because we get the square root of 1 squared plus 1 squared. And the square root of 2 is roughly what? 1.4 is roughly the square root of 2. And then this second vector is going to be 5 squared, which is 25, plus 10 squared is going to be, plus 10 squared is 100. So that's going to be 125. And the square root of 125, calculator tell me? 0.18. 11.18. Okay. So they have 1.4 multiplied by 11.18, and then you can just work it out. I don't need to go through the rest of it. Does everybody kind of do that? So anyway, the point is you can type these numbers in here, and then you get the inverse cosine of this, and hopefully you get the answer of 72 degrees. We're going to do one more, because I want to illustrate a point by looking at different vectors in different directions. Does everybody get the whole process?
So the top line is A plus B, not A.
It's A, it's the dot product between A and B vectors, and on the bottom line it's the length of one vector multiplied by the length of the other vector. Alright, so we end up with...
I don't think 72 is right.
Sorry?
72 isn't right.
It's not right, yeah, it could be wrong. Wrong. So when we get A dot product with B, sorry, what did I get? I got 5, so sorry, it shouldn't be 15 on top. What should it be? It should be 50. Sorry, you're absolutely right. Nicholas, you're right, it was multiplied by, I added them, so I made a mistake. It should be 50 on the top line. Shouldn't it? Yeah. Because I've got 1 by 5, 1 by... How do you do add them? Huh? Sorry, it's 15 on the top. Do add them. You add them, sorry.
Forward.
Can you write it at the top product?
Sure, the dot product is basically A dot X multiplied by B dot X plus A dot Y multiplied by
Yes,
B
that's
dot
30.
Y. Huh?
There's 30 then. So A, so
So
it's 1 by 5 and 1 by 10.
Plus
Plus 1 by
10.
5 and 1 by 10.
Sorry?
So that would be 1 by 5
Yeah.
plus and 1 by 10.
Yeah.
No, that's it.
You don't multiply them two or square them. You don't square them or anything like that. Yeah, it's just 1 5 plus 1 10 is 15.
Is it always written like that, like A dot B?
A dot X multiplied by B dot X plus A dot Y multiplied by B dot Y.
Just the dot product is always...
That's what the dot product always means.
Multiplication of both.
Yeah, you multiply the X's together, the Y's together, you add the two, and that's called the dot product.
Oh, I didn't know that.
Yeah, is that okay with everybody? So anyway, we discovered this angle. Did we discover an angle for this yet? 25, I think. Okay, so maybe it's 25 degrees, right? What do you think? Just guessing? Come on,
No,
guys.
that's it.
It is definitely 25. Right. Let's do one more. Let's see if we can discover a pattern. Let's again take the vector 1, 1, and this time let's take the vector over 2. So 1, 1 is going to be that vector. So let's take over 2 and down minus 3. Try those two. In fact, just to make sure it's definitely going to work, try minus 4. I think that should work. Hopefully work.
Is that 2 minus 4, is it?
Yeah. And you can draw it out and see if your answer actually, rings true. What you think should be. Is the second dot product number, is this number here going to be a positive or a negative number when I evaluate it? Never mind even if the numbers are right. It's going to be positive or negative. Yeah, but sure thing, never mind. Even before I go and work out the angle negative, it's going to be a negative number. Now, do you remember the dot product we did a couple of seconds ago? Is that a negative or a positive number? Draw out those two vectors. There's the vector 2, there's the vector 1, 1. Okay, 45-degree angle vector. Here's the vector 2 and minus 4. Over 2, which is going to be there, and up minus 4. So maybe like right there. That's not even a good one. It's going to be more like there. What does that angle look like? Is it anything interesting?
Almost a right angle.
What's that?
Right angle.
Well, it's in fact it's not meant to be a right angle, but it's actually, is it bigger than a right angle or less than a right angle? It is bigger than a right angle. And definitely you can see, just even from thinking about those vectors, it has to be bigger than a right angle. You know, if it was going to be exactly a right angle, what would this need to be? 2 and minus 2. If it was 2 and minus 2, it would be a right angle. 2 and minus 4 is definitely bigger than a right angle. And so therefore, here's the rule we've just learned, right? If A and B are perpendicular, when we dot product them together, we get a value of 0 if they're perpendicular. If the angle between A and B, if the angle is A and B angle is greater than 90 degrees, when we do the dot product, are we going to get a positive or negative number? We will get a negative number. And if we get the angle between A and B, if it is less than 90 degrees, we will get a positive number, okay? So what we've discovered is that we can tell something about the angle without even doing the inverse cosine thing. All you need to do is do a multiplication and an addition. Does everybody see that? You can multiply the vectors together. You know, you don't even need to calculate the lengths. To know whether the sign's going to be positive or negative, or whether it's going to be equal to 0, you don't even need to calculate the lengths. You can discover certain things about the angle between them without even doing the inverse cosine operation, just by multiplying the two vectors together in this really cool and amazing way. Isn't it amazing? Okay, I think it's amazing. I think it definitely is amazing, personally. Because you can use it to solve all kinds of interesting problems, right? Do you want to solve an interesting problem? Or do you want to take a 5-minute break? Let's take a 5-minute break. Let's come back and see if we can use this property that we've just discovered to do an interesting problem for games. Yep. For the one or two who Skyped off to Google. So yeah, first little thing, if I wanted to calculate the length of the vector, if I wanted to calculate the distance from A to B, well, this is kind of an obvious one, right? When you think about it, if you wanted to calculate the distance from 8 to 10, what's the distance from 8 to 10? It's going to be 2. And how did I know that? I took 10 and I subtracted 8 from it. Alrighty? If I wanted to calculate the vector that if I was at A and it would bring me to B, it's the same thing. It's just going to be B minus A. And if I go A plus B minus A, what do I get? Okay, think about it in these terms here. If that was A and that was B, and if I took A plus B minus A, what would I get? I would get B, obviously. You think about it, right? B minus A, and this one here is going to be what? 8 minus 10, which is going to be? Minus 2. Alright, so 8 minus 10 is minus 2. And then if I take A plus B b minus a minus 2, what do I get?
8.
I get 8. And what's 8? It's b. Alright, does everybody see that little simple bit of arithmetic, right? The same thing applies in vectors. If I wanted to get the vector that if I add it to a, it's going to bring me to b, I take b minus a. So that's going to give me that vector that will bring me there. And then the length of that vector is going to be the distance from a to b. So the length of the vector b minus a, or a minus b gives you the length. So there we go, we can calculate the length. Is that any help to us? What will I do with it? Alright, let's even get into the normalizing. Well, so I could normalize that vector, say b minus a, couldn't I? I could go, the vector b minus a, let's call it c. I should write one bit out more here. I could call that vector c. So if I was to say the vector c equals the vector b minus a, I could then do c equals the vector c divided by the length of the vector c, which is the normalizing of that vector. Ugh, big deal. What have I done now? Have I progressed a little bit further, or have I nailed the algorithm yet? Possibly. I mean, I could use that if I wanted it. It's one way of doing it. Anyway, back to the problem. Am I in front of or behind, or what's the approach? Calculated the length. Do I even need to do that? Maybe? What do you guys think? Okay, so what's the algorithm? Don't be quiet, shout it out. It's obvious. What am I dotting with what to get what? I would say a few people know this and they're just not saying it. I want somebody who knows it to say it. If you don't know it, it's cool. It doesn't matter whether it's the right answer or not. We're all adults here. We're all working together to try and learn games programming together as a team. Come on, you've all had pull requests accepted into BG already. You're awesome. So what are we dotting with what?
The look vector and the c vector.
What's that?
The look vector and the c vector.
Sure thing. Okay, so if the c is equals to b minus a, if I was to dot the vector L with a minus b, which we said previously was the c vector, we don't even need to divide by the lengths in this example. I just know that if this value is positive, what does it mean? It means b is in front, because it means this angle has to be less than 90 degrees. Remember we said that? If this angle is, if this dot product thing is less than, if it's greater than 0, it means the angle is less than 90 degrees. You don't even have to calculate the angle. So L dotted with a minus b, if that is greater than 0, then that means I am in front. And if it's less than 0, then that means I am behind.
Shouldn't it be b minus a?
What's that?
Shouldn't it be b minus a?
Yes. Oh God, yes. That is going to be a completely different vector. It should be the vector b minus a, 100%. Because the vector a minus b is going to be that vector going in that direction over there, so it has to be that one. Does everybody see that? So now we have a very simple algorithm for calculating if one object in the game is in front of or behind another object. We don't even have to calculate the angle. All we do is we take, the vector that brings you from your position to the other guy, and then you get the dot product between that and your look vector, and then you know if you're in front of or behind. So we will do this in the lab next week, right? Is that okay with everybody? Everybody now buy it? Do you kind of understand this algorithm? Everybody? Yeah? Smile if you're happy. You know it. Cool. Cool. Okay, I just need a bit of feedback because I need to know if I'm going too fast or too slow, but everyone's kind of understanding it. So the other problem then I had was actually, is B inside A's field of view or not? So here's the field of view, right? There's the field of view and it's 30 degrees each side. If I actually calculated this angle, I could compare that angle with 30 degrees. And if that angle was less than 30 degrees, it would mean I was inside the field of view. If that angle was greater than 30 degrees, it would mean I was outside the field of view. You follow all of this? So then I could just do the extra step, right? I could do the extra step of calculating the minus a, using the length that I previously calculated, dividing by the length, getting the inverse cosine, and I will find that the numbers actually, comparing it with 30 degrees, I know I'm actually inside the field of view. We'll do it in C++ right now. How about that? Don't get too excited now, okay? So we'll do it in C++ just to prove that it works. And hopefully you'll see the algorithm and the steps involved, okay? So, I'm fire up my laptop. And you know what? For the hell of it, let's put up some numbers for these problems. Let us say that A is equals to the vector, you know, if this is going to be this thing here. Let's say that A is going to be equals to the vector, say over 10 and then 15. Let's say that A's look vector is going to be equals to the vector 1 and 0, 0 and minus 1, which means what way is A kind of looking? It's going to be looking straight up. Okay, so that's its look vector. Let's imagine I have this vector B, and this vector B is located at over 50 and down 60. And I want to know is B inside A's field of view or outside of A's field of view. Sound reasonable? Does everybody see that this is the problem we've just done in, we've just worked out the algorithm? Right, that's coded in C++. And if you have a laptop, you can fire it up, right? Anybody want to ask any questions?
Sorry, Brian, is it
Yeah.
0 minus 1, I thought, would that be not directly pointing down?
Not in this example. Minus 1 on the Y is going to be up.
Origins top left.
Because the origin's the top
Oh, okay.
left. So that means basically I'm adding to the Y to go down and I'm subtracting from Y to go back up again.
Does it matter if the angle is positive or negative?
Yeah, 100%. Definitely.
Outside.
If you're rotating the sprite 100%, it matters, yeah. Well, for the 30 degrees, it doesn't matter. For this
No,
problem,
no.
for this one, it doesn't matter, no. But yeah, definitely it matters.
Squaring it, sorry.
What's that?
Why doesn't it matter?
Well, because we're looking at the magnitude of the angle rather than the direction of it. If it was minus 30 degrees, it would be on this side, and if it was positive 30 degrees, it would be on this side. But you know what? I actually think the answer ends up as being positive anyway. I'm pretty sure it's always going to be positive. What's that?
Square something.
I'm pretty sure the angle, you get a positive angle regardless of which side you're on, you know? Or you might, we'll have to look at that in a sec. It's a good question, right? So I'm going to create a new console app in Visual Studio. Let's switch that thing on. Come on. C++. And this is the last thing we'll finish with this today, okay? General empty project. Vectors. Is that thing coming on? Oh yeah, there we go. So should I turn the lights down? How many people are going to code along here? If you have a laptop, code along. Otherwise, just take some notes, right? So I'm going to right click on this. I'm going to click add new item. And I'm going to add a C++ file. I'm just going to call it source. Doesn't really matter. Here's my C++ file. Okay, so for this project, what's the first thing I'm going to type? C++ hash include something. What should I hash include? Yeah, you know what? We're going to use the streaming I/O, which is the C++ way of doing I/O. When you see it, you just go, yeah, that's how we used to do it in first year. That's printf, but this is how you do it in C++. It's slightly nicer. And it's actually I/O stream, okay? And then no H file. Now, because we're going to use the GLM maths library, what do I have to hash include? Yep, we'll do glm/glm.h. And I'll come up to Visual Studio, go into my project properties, go into the configuration properties, the directories, and for include directories, I'll add the path there. Projects, dependencies, GLM. That'll do. Hopefully that red underline should disappear now. Build. Okay, so let me just double check that value. Project properties, include directories. Edit. New GLM. GLM. That's correct, isn't it? So why is it not disappeared? Maybe it will disappear. GLM. That's glm.hpp. Pay attention, guys. You need to watch what I'm doing here, right? It's glm.hpp, okay? And then we'll go void main, and we'll make it a C++ program. Okay. Let's declare some vectors, right? Let's go glm : vec2. Just going to declare a vector, and let's call it A. Call it A like that. and then GLM colon vec2, and we'll call this one B. And then we had another vector for the look vector, didn't we? So we have this vector L. Okay, so let's do some assignments. A is equals to, and this is how you do the assignments, GLM colon vec2. So what was the values we gave to A? 10 and 50. Okay, and then we have B, and we gave the values. What did we give to B? 50 and 60, yeah? Okay, and the look vector for A I said was going to be equals to 0 and minus 1. Fair enough? Everybody looking at that? Can everybody follow this? Quick one before I go any further, how would I improve that code a little bit? Yeah, could you share pointers? Maybe a bit of a pain because these are only going to be just declared locally and thrown away anyway, so it might be a bit of an overkill. How would I improve that? Isn't it a bit wordy? Is there too much code? Can I do less code? I can basically do it like this, you know, just to show you. You can go GLM, blah, 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 take that there, and then just go A equals. Quick one for you guys. What's happening there when I do A and B? What am I calling? Now, what do you think is happening there? Just a quick one in C++ terms. What's happening? What am I doing? What's happening here, do you think? What am I calling?
Constructor.
The constructor. Okay, perfect. So I'm calling a constructor, this is just calling a constructor, and then it's copying its value into this, and that's just a way of doing it all in one line. Alrighty, hopefully everybody knows what constructors are at this stage, do you? Cool. Alrighty, so I've got A, B, and C. First problem, in front of or behind. So what did I say I needed to do to calculate the in front of or behind? First thing I need to do is maybe do another one, and call it C, is equals to the vector B minus the vector A. And that's how you would write that in C++. So C++ is one of those nice languages like C#, in that you can write things like this because what does it support? It supports operator overloading. You can't write this type of code in Java, but you can write it in C++ or C#. And this will call a method, or call a member function on B, pass in A as a parameter, and return it. Remember we did this in, for you guys it will be C++, we C++ in second year. Or we did C#. So you remember we did this in C#, we made vector classes. It's the same kind of idea, right? So there we go, that's the vector C. And then I said I've got something like float, in V, C, is going to be equals to the dot. So the dot product is GLM : dot. And then you pass in the two things you want to get the dot product between. So I want to take the look vector and I want to take C. So I get the dot product of those two guys, and then I've got an if statement to say if the INVC is a positive number, what does that mean? In front. That's behind. Okay, we've got a little compiler error at this stage. I'm going to show you how you fix this compiler error. What we do is we put the using statement, using namespace std at the start. Do you guys remember we did namespaces in C#? std. Do you remember we did namespaces? What's a namespace? In C#. Collection of classes, right? So the C out is in the namespace of std, and therefore you can either write, if I didn't put that using namespace, what could I put up there? std : and that means use the std which will resolve to that namespace. So either one of those is okay. Now, does anyone find this code in any way confusing, or does it look kind of reasonably okay?
You say in front.
Definitely. But just in terms of like the syntax, okay, so you can see I'm calculating the inverse cosine from the dot product of those two vectors, and then what about the C out thing? Is everybody clear on what that's doing? Don't get too hung up on the fact that it's different to C sharp or whatever. It's C out, and then this is going to print this thing, and then end L is going to print the end of Y. That's how you do kind of console Y on C++. Is that okay with everybody?
Can you do it statements without the curly brackets in C++?
Of course, you can, yes, but we never do that. We always put the curly brackets in. It's just good programming practice to always put the curly brackets in like that. Same sort of stuff to do with making your brackets line up and all this kind of important. Okay, so that's pretty cool. Let's run this in the debugger and see what happens. What do we think the answer is going to be here? Is it going to be in front of or behind? So we have 50, 60, we have 10, 60, and we have a look vector of 0 and 1. Do we think it's going to be in front of or behind? Huh? How many people say in front of? How many people say behind? Okay, well let's run the program first. Let's work it out in our heads first before we do it. So we've got over 10 and down 50, so that's over 10 and down 50. Look vector is straight up like that. And this guy is over 50 and then down 60, so over 50 and then down 60. So it's going to be behind or in front? Behind. Okay, it's going to be in front. Behind. So if it doesn't come out as behind, then the maths is wrong. So let's try. Set a breakpoint here. Function F9, function F5 in Windows. So now we've reached this line of code, you know. You can hover over A and B, you can see what their values are, see what A tells you would be. And then I'm going to hit F10 to step over, and it's minus 10. So amazingly, it has worked. It's awesome! Woo! Okay. Is everyone excited?
Yeah.
Good. We have now started with maths. We've ended up with a C++ program where we can just read coding. Let's try the next bit of this problem. Inside the field of view or outside the field of view? What would I do to complete this problem? The inside the field of view, outside of the field of view problem.
Multiply the length of L and B minus A. Length of B minus A.
Okay, so let's get the length maybe of the B minus A vector, which we call C. So to get the length of the vector, we use GLM : length. So that's going to be the vector C. Okay. Let's call this length C. It's going to be GLM : length. So now I have the length of that vector. What do I do basically to put all this into the little equation? What I have to do is take the dot product on the top divided by the length of A and the length of B. But what's the length of L? The length of the look vector is going to be 1. So we don't need to really take that into consideration because multiplying anything by 1 is itself. So there's length C. So I can go float theta is going to be equals to, and this is how we do the inverse cosine, GLM : A cos. And I have the dot thing up there, I call it inverse cos. Or maybe I should just have called that top line, divided by length C. And then that should tell me the actual angle. Alright, because I get the inverse cosine. Oh, hang on a sec. Inverse cosine. Yeah, I've done the dot product of those two vectors over there. Is that okay with everybody? Everyone follow what I've done there? You need to give me some feedback, say if it's okay. Alright, cool. So then that's the angle. And then I can check to see if the angle theta, which is in radians, okay, because those methods are going to be in radians, is less than 30 degrees. So I can go GLM : radians for the value 30. If that is less than that, then I am inside the field of view. Otherwise, I am outside the field of view. Okay, so what should we happen here? Are we inside the field of view or outside the field of view? We're obviously outside the field of view, aren't we? Because, you know, I'm behind, so I couldn't possibly be inside the field of view. So let's see if this works, right? So there's that one there, function F9 to toggle the breakpoint there. And the function f(y) is running the debugger. So here we go, here's len c. So len c function f10 is going to be a negative number. Theta is the inverse cosine of one of those guys. So I end up with theta as being 1.81 radians. So hopefully it's going to be less than that. And I'm outside the field of view. So incredible. It has worked. Is everybody really happy? It's like we can go home, but we've learned a cool thing today. We've all come on a journey. A journey where we started with some lines and dots on the screen, and we learned some maths, and eventually we ended up in a C++ program that does something cool.
What if it be like if you? Because what happens if the angle is like 300 degrees? What's the?
Great question.
What's going to be the result of the?
If it was 300 degrees, in other words,
300
if it was the exterior angle or the interior angle, that's a great question.
Oh yeah, if it was like 350, then it would be within the site. But whether it be the
Yeah. So that's a really great question, actually. Here's the problem, right? Here's the question that Camila Kajun is asking. Located here, looking this way, imagine that the character thingy is over here, and you get the angle between them, and you get this big angle over here. Is it inside? Is that what you're asking? Or even if it's up here?
yeah, like up there.
Great question. So you think that you could get an angle back which is going to give you this one?
Yeah, and let's say this would be 340.
Interesting.
degrees.
There's
And-
two ways we can do this. We can either put some numbers in and we can see what we get, or I can just tell you. Oh, you're so no fun. No fun. The answer is, when you use the dot product to get the angle between those, you always get the interior angle. You will never get the exterior angle. So you can see that you're inside the field of view. If you get the dot product of those and you get the angle, you always get this small angle rather than the big angle.
Is
But
the
that actually causes problems.
is the
You
angle
know,
positive or negative? Like, is it always positive or?
I think the angle is always a positive angle. I'm almost certain the angle is always positive. Great question. I think it's always positive. Yeah, cool. So we can use vectors and we can use C++.
Field of view. Is
Yeah.
yeah. Calculate that. Another way, say it's looking straight up.
What's that?
Say the
look vector thing, yeah.
Say it's looking straight up. Okay.
Mm-hmm.
Is the field of view being calculated from straight up to whatever angle it is? So it's like you can't see any way to the left. Any way of getting it going straight through the middle
Sure.
angle.
That is a way of doing game AI. That is a way of faking real human field of view in a computer game, which is very, very common. So obviously humans have peripheral vision, and our vision is much more complex than that, but it's quite common in a computer game. You can even do it in game engines when you're setting up things. You can say this is the field of view of this character, and you can say it's 30 degrees or 90 degrees or whatever, and it will just use that value. So it's a way of faking it. The other thing that we didn't bother was basically distance calculation. So you might sometimes want to calculate the distance. And here's the last thing. I knew there was one more thing. Right? This is like an Apple product announcement here. There is one more thing. What if the length of A and the length of B is equals to 0? If the length of A is equals to 0, and the length of B is equals to 0, how does that change that little equation that we learned earlier on? Sorry. 1. Length 1. How does that change the equation?
It breaks.
Hmm?
You divide by 0.
Sorry, I meant to say 1. Sorry.
Okay.
So we divide by... when you divide by 1, what do you get? You get the number. So that changes our equation. So what do we call these special vectors that have a length of 1? Yeah, they're called unit vectors, okay? So if A and B are unit vectors, then theta is equals to the inverse cosine of A dotted with B, and you don't have to divide by the length or calculate the length if A and B are unit vectors. Look vectors are almost always unit vectors. Unity calls look vectors. Vectors, anybody know what they call them? Look vectors you see in a lot of books, yeah, Unity calls them the forward vector. And then also Unity has things like the right vector and the up vector, and we'll look at next week how we can calculate the right vector and the up vector given the forward vector by using another property of multiplying vectors called cross product. So anyway, yeah. So you see, so sometimes when we're doing C equals B minus A, sometimes afterwards we will normalize C because it makes the subsequent calculation slightly simpler because we don't have to divide by the length. Does everybody see that? Okay. So we're almost done. Will you take out a page, everybody?
You're on the program with B is in position of 1.5. Would say that's in the view.
We'll, you know what, let's do it. While you're doing this, I will do it. Okay, we'll actually try it out. I want you to write on a page a summary of everything that you've learned today. You know, a few bullet points. What have you learned today? Okay? Could be the git stuff. Could be the vector thing. Could be the trigonometry thing. Could be how to get GLM working in C++. These are all the things that hopefully you guys know at the end of today. And it could be that sort of process of writing little algorithms to solve problems in games using trigonometry and some vectors and maths and stuff. And then let's do this last thing, which is just to put something in so that we get it inside the field of view. Lee, so if that's 1050 and the other one is 5060, can you give me a value that I can change B to, which I pretty much guarantee is inside the field of view?
1040. Oh, no, not 10, sorry.
So yeah, you know what? Draw it out and put some numbers in there. Give me a number which I know is definitely inside the field of view.
1240.
Probably not inside. Look at the look vector. You need to know what the look vector is. I'm looking straight up, right? So I've got 30 degrees either side of that. So pick a number which you know is definitely inside that triangle. Tell you what, don't tell me. Think about it and then tell me. Huh?
11, 20.
It's still not inside the field of view. Like, what's that? Sorry, 11 and over 20. 11 over 20. Yeah, sorry. Yeah. I've had a long day too. So 11 and I have a cold. That's my excuse. Over 11 and down 20. Yeah, so it's going to be up from this vector and just over slightly. So this is probably inside the field of view. Sorry, you're quite right, Lee. My apologies. We need to, just watch what I'm doing and make sure I don't make mistakes. So shift, let's do this control function F5. Loading. This thing. This time when we look at it, I think it should say in front. So it says in front. And then let's see if I'm inside the field of view or outside the field of view. Sorry. Function F10, step over. Yeah, there I am. So now I'm inside the field of view, so it worked.
Now, could you run it with 9 and just keep Y the same? So the exact same, so run it with B is 9.
Yeah, cool. So B should be 9. So in other words, the angle the other side. Yeah, because this is going to tell us whether we always get positive or
I want
negative
to see
angle.
if it's gone, if the front has gone straight through the middle of the angle, instead of just taking it from the front, from the 0 angle.
Say again?
If the view has gone both sides of the angle.
Oh,
rather than
sure.
just taking it from
Yeah,
the
yeah,
front.
because that will tell us, if we've got positive angles or negative angles back from that, right? So shift control function B, build, build, and control function F5 to run in the debugger. And we get the, control function F5 to run it again. So we get to this, what's happening here? Oh, no, it's just F5. Sorry, function F5. Just get it to stop, right? So then function F10, step over, theta, and now we're still inside the field of view. So theta, even though it's a negative angle, you can see, even though it's rotated in this way, the theta is actually that way. So it'll always return a positive
Can you
angle.
find out 980?
What's that?
980, let's say.
Sure.
Good job.
9 and 80. 9 and 80 is going to be behind, isn't it?
Yeah.
Inside the field of view. So it always works. We have a pretty foolproof way, and that's great that you guys are throwing up vectors to try, because if you were trying to write unit tests for this, that's exactly what you would do. You would put in a load of vectors that you can pretty much guarantee are going to be either in front of or behind or inside or outside the field of view. Unit test the hell out of it and make sure that it works. Alrighty, I think that kind of wraps it up for today. Yep, 1700 exactly.